This Explain Everything video is intended as an instructional resource to help teachers more effectively conduct the lesson as described in the teacher notes. The same acceptable use policy restrictions apply to this video as they do to the rest of the curricular materials made available by AMTA. In Unit 6, students use trends in the formulas of binary compounds to deduce the charges of ions in elements 1, 2, 6, and 7. At that time, we put off discussion of what happens to elements in groups 3 through 5. Now that students have a better understanding of the arrangement of electrons in these atoms, we can visit ion formation from an energy lens. The goal is to replace the anthropomorphic language like the alkali metals want to lose an electron so that they have a filled lower level, or the halogens want to gain an electron to complete their valence level, or even the noble gases are happy because their valence level is filled, with a treatment in terms of what is energetically favorable or unfavorable. Pictured here is the solutions to Unit 11, Worksheet 3. The goal of this Explain Everything project is to point out some of the key features to emphasize in the discussion. First, we have to distinguish the values used to characterize elements as either having a weak or strong attraction for electrons. It is true that these values are arbitrary, but they're consistent with other known data about these elements, and you have to have some sort of cutoffs. The answers to these two columns is relatively straightforward. If the attraction for electrons is weak, as characterized by a low ionization energy, then the elements are likely to form positive ions. If the attraction for electrons is strong, as characterized by an ionization energy greater than 10 electron volts, then the elements are likely to attract electrons to form negative ions. Now we'll explain why these answers are 1 for the alkali metals. Each of these elements has one valence electron, which is weakly held by the nucleus, so it is easily lost. But why can't these elements lose 2 or more electrons? The answer is, after they've lost their one valence electron, any subsequent electrons would have to be removed from a lower energy level for which the nucleus has a stronger attraction. Therefore, we say it is energetically unfavorable for these elements to lose more than one electron, and they tend to form positive 1 ions. Let's examine these values of the table for the halogens. Each of these elements has a relatively strong attraction for electrons, but why do they gain just 1? The answer is they have only room for 1 more electron in their valence level. Any additional electrons would have to occupy higher energy levels for which the nucleus has a weaker attraction. Therefore, we say it's energetically unfavorable for these elements to attract more than 1 electron, and they form ions with negative 1 charge. We think this locution is superior to saying that these elements want to gain 1 electron to complete their outer level, as if having a completed outer level is something special. Now we're going to explain these answers in the table for the noble gases. Since each of these elements has a strong attraction for electrons, we have to say yes for all of them. Students might object to this language, saying that these elements don't form ions at all, but it's not because these elements don't have a strong attraction for electrons. Instead, the answer is their valence level is full and cannot accommodate an additional electron. Any additional electrons would have to occupy the next higher energy level for which there is a weaker attraction by the nucleus. Therefore, it is energetically unfavorable for these elements to attract additional electrons. Now we're ready to take a look at the elements in group 4. Here the attraction of electrons range from strong for carbon to intermediate for silicon and germanium to weak for tin and lead. Carbon, which has room for 4 more valence electrons, could attract as many as 4, forming a -4 ion, although this is very rare. You only find it in compounds like tungsten carbide, W2C. Silicon and germanium with intermediate attractions tend neither to lose electrons nor gain electrons. We call these elements metalloids. Now we'll examine the tendency of tin and lead to form either a +2 or +4 ion. Recall that in Investigation 1 we plotted the successive ionization energies for the first 20 elements. Here is silicon in group 4. Like silicon, tin and lead have 4 valence electrons. 2 of these, though, are more easily removed than the others. So it's possible for these elements to form ions with charge +2 or lose all 4 valence electrons and form +4 ions. Similar reasoning can be used to complete page 2 of this worksheet. Note that beryllium with an intermediate attraction for electrons is unlikely to form either a positive ion or a negative ion, and it's generally not included as the +2 ions as the other elements in its family. We next examine the trends in first ionization energy for elements in group 6, which range strong for oxygen and sulfur, but intermediate for selenium and tellurium. These latter elements are considered metalloids. Similarly, in group 5, the attractions of the elements for electrons range from strong down to intermediate to weak for bismuth. Therefore, these elements go from nonmetals to metalloids to a metal. Now we have an explanation for the stair-step line demarking the metals and the nonmetals, with elements along the margin being considered metalloids or semi-metals. As we said before, nitrogen and phosphorus have strong attractions for electrons, tend to form negative ions, and are considered non-metallic. Bismuth has a weak attraction for electrons, tends to form a positive ion, and so it's a metal. Arsenic and antimony have intermediate attractions for electrons and form neither positive nor negative ions and are called metalloids.